In natural selection, the most fit organisms survive and reproduce more, and leads to changes in groups of organisms over time. But the exact pattern that occurs and as to how the population shifts is referred to as a pattern of selection. And there's actually different patterns that can occur that we'll take a look at. And this is a list of some patterns that we can see. So we'll start out with directional selection. So in directional selection, it gets that name because one extreme phenotype is selected for. So in a particular environment. So if you have, for example, light and dark, either the light extreme is favored or the dark extreme is favored. And then that becomes more prevalent in the population. So it tends to decrease variation and select for extremes. The patterns of selection are oftentimes well understood when we can look at like a graphic representation. So we can take a look at direct selection in mice here. So our starting population, so this is before selection and this is after selection. Our starting population has mostly light-furred mice, and we can see the image here. There's mostly light-furred with some dark. And then we do have some dark ones, okay? So over many, many generations, there's a population that's exposed to a dark environment. So this is a dimly lit forest. So remember, this is always determined by the environment. So imagine that this environment had changed. And so now there was an advantage to being dark colored because it was a dimly lit environment, and the dark one was it was harder for predators to see. And so over time, we see a shift towards mostly dark furred. Okay, so extreme phenotype is favored here. And in this case, it's dark. Okay, so in this example, we went from having mostly light to mostly dark. But you could also have a population that started out like this, where mostly all of your mice were in between, like maybe they were gray. Okay, and then we saw a shift towards mostly dark. That would still be directional selection. You might also have a population that started out like this and shifted to mostly light, right? So if this is your before, this could be your after, okay? So your before can look different. When we say directional selection, what we mean is that the end point is the same. Either one extreme or the other is favored. Your before could also look like this. You could have even of everybody, right? So if you had, 10 light-colored mice, 10 gray-colored mice, and 10 dark-colored mice, then your line would look like that. And then you would see a shift that way. So again, the before isn't what matters. It's the after that matters. And the after should have a peak at one of the extremes, either the dark extreme, the light extreme, or whatever the trait happens to be, okay? Because directional selection selects for at one of the extreme phenotypes. In stabilizing selection, we see that the intermediate phenotypes are favored. So in this example, we're starting out with a lot of variation, and then we're seeing a narrowing. So this is after selection, this is before, and after selection has occurred over many, many generations, most of our birds are ending up with their phenotype more in the middle. And so this is referred to as stabilizing selection. In this case, the trait is eggs. So if you think about a bird that's laying eggs, you have birds that lay somewhere around the middle, some that lay very few eggs, some that lay a lot of eggs. And so if you lay too many eggs, you can't take care of them. But if you lay too few, you don't have as many offspring. And so evolution favors, or natural selection favors, that balance. As many eggs as you can take care of. And that's this intermediate phenotype. And so we see selection of clutch size, that's the amount of eggs in a nest, in this direction. And like what I said with directional selection, your before graph can take different forms. It could look like this, or it could look like this, okay? Or it could look like, let me change colors here. It could look like this, right? Again, the after is what matters. The after, we're seeing everybody come to this intermediate phenotype. Notice in all my before graphs, though, I had to have variation, right? So you always have to have variation in your starting point in order to get natural selection to occur. Or in other words, whatever is your favorite phenotype has to be present in your initial population, okay? There's other traits that have experienced stabilizing selection. Human birth weights are another good example. Human birth weight is a relatively narrow range if the baby is much larger or smaller than a certain size. So if they're below about 6.6 pounds or bigger than 8.8 pounds, there's greater infant mortality. The reason being that if the baby's too small, it doesn't have enough resources and warmth and things like that to survive outside of the womb. But if the baby's too big, it has difficulty getting out of the womb without harming itself or the mother. So we see very narrow birth weights in humans as well. Okay, so stabilizing selection, if we think about how it affects genetic variation, so think about how much variation is here versus here, and hopefully you see that because it favors an intermediate, it oftentimes reduces the amount of variation, right? So we lose these variants and these variants. So that tends to show a decrease in variation.